So, good evening, everyone. So, we will start today's live interacting session within a few minutes. I think the screen is visible. So, after 2 minutes, we will start today's session. So, please wait. So, first of all, I will welcome all you to this live interacting session, which is our seventh session on this course, this conduction and convection heat transfer. So in these courses is being taught by Professor Chakravarti and Professor Shom. So I hope that you all of you have gone through these courses, and this course is quite vital for your academic or for your if someone of you is interested in research. So this course is quite vital. So I am Niloy, your TA for this course, and I am a PMRF scholar from IIT Bhubaneswar. So before going into this today's session and what are the topics we will today we will deal. So before this we will discuss about this course and why this courses is essential. So in these courses what you will find is that you will find the basic concept of this conduction and convection. Though radiation is also a mode of heat transfer, but we will not be dealing with this. And the next is that we not only deal with this heat transfer mode, we also try to implement how the underlying physics or how this governing equation of the laws can be relate with this rate of heat transfer mode. Like if during the fever you see our body temperature rises and why such thing is happening, and similar types of question which arises in your daily life, so you can counter with this fundamental concept or this equation. So that's why this courses is important. So before today's session, so today's session is a little bit new to you, most of you. So I suggest you, if someone of you misses this earlier courses, please go through this the last 6 session, or even I suggest you to follow the lecture given by Professor Shom and Professor Chakravarti. So because you need this fundamental concept to move ahead in these courses. Okay. So what we will be dealing with the today's session. Before this, let me recap what we have studied in the earlier session. So in the earlier few sessions we have discussed about the conduction mode of conduction and how to implement this 1D conduction equation for different bodies, and after that we have studied how to solve numerical based on this 1D conduction equation, and analog circuit corresponds to this conduction and the convection, and also most importantly we have studied about this convection, fundamental of this convection, and how the fluid velocity and all other parameters affect this convection, right? So these are the concept already we have studied in the earlier classes. So in this session what we will be doing, we will be studying this fundamental of the fluid mechanics. Basically, in the earlier few session, we generally deals with this energy conservation equation, or the mainly this 1D conduction equation, right? So from this energy balance equation, we have derived this. So now, as in the convection, majorly it depends on the fluid velocity. So it is quite essential for us to understand what are the properties of the fluid, right? So to understand these properties of this fluid, we need to understand this conservation equation, like this conservation of mass, conservation of uh, energy, and all these things we need to deal, right? So, so our main motto is to implement the concept of the fluid mechanics into this concept of convection and conduction, though mainly for this convection. Before starting this thing, first let us understand two concepts. So which I think that you have found. This is the Lagrangian approach. Next is the Eulerian approach. So these are the two fundamental approach in fluid mechanics. Why we will be going to study this approach is that I hope that you have understand this concept of control volume and control mass, right? So if you talk about a control mass basically means if I talk about a particle which is having a certain mass. So if you are observing whole the body at a time, so this is we known as this control mass. But in case of control volume, we are not dealing with the whole body. So we basically is taking a part of this body, which will and we will study the properties of that part, and that is known as the control volume. So basically these two things related to these two things we will be studying this Lagrangian approach and the Eulerian approach. So in the first we will be dealing with this Lagrangian approach. So in this approach what we will be dealing, we will analyze the basically in this approach we will analyze the fluid motion, and by tracking individual fluid particle as they move through the time and space. So like for example, what I can say this is a river. Okay, so if you see a what I say, this is a wooden block. So this wooden block is flowing through this river. So if you are observing only this wooden block, your main focus is this wooden block. So it will change, its position will changes with time, but your main motto is to track this individual wooden block. So that is your motto. So to analyze this motto, we have to deal with this Lagrangian approach. That means we will have to track the individual particle. So the particle will move with the space. Space means your position, and time means with this is the temporal variation I am talking about, right? So basically here if I represent this is should be a function, here x should be a function of, sorry, basically here a point should be represented at x comma y comma t. So in each interval, say at time t equal to 0, so the position may be x equal to 0, y equal to 0, z equal to 0. Similarly, at t equal to say t naught and t1, similarly its position will change, right? So that is our Lagrangian approach. So what we can say that this approach, the main purpose is to analyze fluid motion. How we will analyze fluid motion? By tracking individual fluid particles as they move through space and time. So that is our Lagrangian approach. So any confusion up to this, please let me know. So what are some of the properties that we can track? Suppose if I talk about this particle, we can track its say we can track its velocity, temperature, pressure, right? So that are some of the property we can track. So we can track properties like its position, velocity we can find at every point, or like temperature, like pressure, and many more. So these are the important thing that we will find in your BTech level. Okay. So so the important thing is that if you have to find the velocity of this particle, say this is a particle at time t, say at time initially it was at this point, right? I just consider 1D. Let us assume a 1D problem. That means x, y and z is not there. So in this 1D position, what you see at initially it is at x naught position, and at after time t1 it is at x1 position. So if you have to find out this velocity, what is velocity? We know it is dx dt. That means it is the change in the distance. What is the change in the distance? That is x1 minus x naught, and the time is t1 minus naught 0. So in this way you can find out the velocity in case of Lagrangian approach. So any confusion up to this, please let me know. So I am moving to the, I hope that there is no such problem. Okay. So I am moving to this Eulerian approach. So this Eulerian approach basically means, if I'm first giving you an example. So this is a river, right? So you are seeing a lot of particle, or say an wooden piece or a leaf is flowing at this position. So your objective is to track only, you are just put a camera here. Say this is your, you just put a camera. So your main motto is to observe only this region. So in this region a lot of particle can flow. So initially a wooden block can flow, and after a few moments a leaf can flow over it, a water bottle can flow, anything can flow over this region. So here our main motto is only specific region, not the particle, right? So that type of approach is known as Eulerian approach. So basically here we will analyze fluid flow or fluid motion by observing. What we will observe here? At fixed position or location in space as fluid passes through them. So basically here the fluid is passes and our motto is only to look at this fixed position, right? So that is our fundamental here. So in these cases, so you see, in these cases, as our motto is only this fixed position. So each and every particle, the property of each and every particle will be different. Say this is particle 1, this is particle 2. So what may be the velocity of this particle 1 and what may be the velocity of particle 2? It will be different. In some cases may be same, but that is very rare. So these properties will change. So how will be the property? This property will be the function of here fluid properties are function of space. Space mean position. Like that means here x, y, z like that, and time. Okay. So if I talk about say velocity, so velocity here should be a function of x, y, z, t. Similarly, if I talk about the pressure, so it should be x pressure will vary at each and every with each and every particle and even with position. Any confusion up to this? Say if I will give you an example. Say you just put a thermocouple here. You know thermocouple which measures the temperature. So if you put a thermocouple here, so if the water is flowing, maybe the temperature of the water is different in each and every moment. So sometime it is cold water coming, sometime hot water is coming. So what will happen? The thermocouple will show you temperature reading. The position is fixed, but the fluid particle is different. So that's why the thermocouple will show different temperature, right? So that is the difference. Here our objective is to only we just in these cases in the Lagrangian approach what we did we just put the thermocouple over this particle or this block and with the as the block is moving the thermocouple is moving. So at each and every point the thermocouple will only measure the temperature of the particle, not any other thing or the fluid. You got it? So that is the basic difference. So as this is a fixed region, so fixed region basically corresponds to your control volume. So this Eulerian approach is also known as the control volume approach, and this Lagrangian approach is your control mass approach. So in fluid mechanics, we basically is dealing with this Eulerian approach. Like what are the sum of the problem that we will study? We will study flow through a pipe or this heat transfer and each and everything. In majority of the case, it depends on the Eulerian approach. So please remember this thing. So which approach you need to study in these courses? 95% of the cases you need to study through this Eulerian approach. So the basic difference, if I talk about, I am again repeating this thing. So the basic difference between these two approach is that in this Lagrangian approach, it only deals with the individual fluid particle. That means all a specific particle it will target a specific particle. Whereas in the Eulerian approach, it fixes the position, right? And in the position, whatever may be the particle flowing over this position, it will track all this particle. The position is fixed, the particle may be different. Okay. So the main thing is that coordinate is fixed. X, Y, Z, this coordinate is fixed in Eulerian approach, whereas this coordinate can vary in Lagrangian approach. So for fluid analysis, which one is easy? For fluid analysis, your Eulerian approach will be easy. The Eulerian approach will be easy. Easy for fluid analysis. Okay. So up to this is the main thing. Okay. So next thing. Now see, our main motto is that in a given problem, so I have talked there are two things. One is control mass and another is control volume. So in order to convert a control mass into a control volume approach, what we need? We need a certain equation to convert this thing. Like because say if I talk about the previous cases, if someone asks you to track each and every particle of a water flowing through a river or pipe, is it possible? No, it is quite difficult, right? So what we need to do, we just have to have there should be some formulation based on which what we can do, we can convert this control mass, that means a specific particle they are talking about, to a control volume approach, right? That means in a fixed position we will be dealing with. So that's why this thing is important. So to solve this, scientists have come out with an approach. So that approach is known as your Reynolds transport theorem, right? This is RTT. So basically it link both the control mass and the control volume approach, or you can say this Lagrangian and the Eulerian approach. The main motto is to convert it into a into a control volume approach. So I think that all of you have gone through this derivation that has been shown in the classes by Professor Chakraborty, right? So I am just writing this same equation which he has written in the classes just for your understanding. So this is the equation. So in this equation, n basically means an extensive property. That means it depend on the mass. Okay, and small n here is the intensive property of n, which will be n by mass, right? So you know rho is the density here. V, this one is your volume. So, and capital V is your velocity field, or this is you known as velocity vector, or N vector is the outward normal vector. So this is the thing. So now I have to understand. We have to understand what are the part of this Reynolds transport equation. So what this part, what is the part on this left side basically indicate? So this part I am talking about. So this part basically represent the rate of change of property of a system, right? See, the important thing here is that rate of change of property of a system. So from this, can you tell what type of approach is this? If I talk about only this thing, whether it's a Lagrangian view or a Eulerian view. Can anyone just guess? Why it is? Can you tell why it can be an Eulerian approach? So the system is fixed. If say you are saying that the system is fixed, so what we have given in the earlier slide, if something is fixed, so if you are targeting a fixed thing, then it is a Lagrangian approach now. In case of Eulerian approach, you will deal with a lot of particle. Only the position is fixed. When in this position, so whatever with the particle, so we will have to track. Only a small, the river is quite large. We will just take a small portion of the river in Eulerian approach. But in the Lagrangian approach, we will deal with only with the particle. So these basically represent the first part basically represent the Lagrangian view. It is the how much the property, any property, maybe it is mass, maybe it is energy. Say if I talk about this mass, so what is the change of the mass of a system? Rate of change of mass of a system. So that is basically the Lagrangian approach or view. Okay. So now on the right hand side, what is there on the right hand side? This first term. So this first term basically is a control volume. Says CV means control volume. So whenever there is a term, say this is the block, this is a block. So this small part is known as control volume, right? So this small part is known as your control volume. So I can write this indicate the rate of accumulation of property inside the control volume. So basically on the left hand side it was the rate of change of property of a system. So that means this the system is the whole body. This is your system, right? So what may be the inside this whole system it is in the first in the left hand side it is talking about this whole system. So what is the changes, overall changes you will observe on this system? So that has been included in the first part in the left hand side, whereas on the right hand side the first thing is that rate of accumulation of the property inside the control volume. Say in this control volume how much the property is getting accumulated. Like if I talk about uh, say if you talk about a jug or you bucket, in a bucket you are pouring water and somehow in the bottom there is a leakage. So what will happen, though you are pouring water, something will be going out or outflow is be there. So what will happen, there will be some accumulation in the system. So that accumulation is dealing with the in this part, right? So the next part is the second is the SCS means the control surface. So what is control surface? So the control surface means, say if I talk about this thing in the surface, so this is a surface now. So if I just take a small section of the surface, so whatever may be the coming inside this surface or going inside that thing we have to look upon. So that's why this is the in this equation also the control surface is taken into account. So it basically represents the net flow of property up to this. Any confusion? Please let me know. Okay. So I hope no doubt up to this. So that's why these two things, if these two things are your Eulerian part or view, right? So that's why this Reynolds transport equation is important because it can convert a Lagrangian approach into an Eulerian view or the Eulerian approach. So overall, what I can say, what does this? So if someone asks you, so this equation you see, most probably 99% of the student will forget this equation, right? So how you will just if someone in any interview or in any viva, if someone asks you, what is the what is the Reynolds transport equation? So you will not be able to write this equation if you do not practice this equation, right? So how will you tell? So no need to write the equation at that moment. If you forgot this thing, what you say, that it basically means whatever be the rate of change of the property of a system. System means this whole thing. So it should be equal to, we have to take a small control volume and a small control surface. In the control volume, we have to check how much is accumulated inside this control volume. And in the control surface, we have to check how much the flow is going inside or outside. That means the net flow we have to check in the control surface. You got it? Everyone got this thing? Okay, I think so. So this thing, I am just writing one thing. I'm just doing one thing. Duplicate. Mm, okay. So next thing, please look up this thing. So now our main objective is to see there are three equations in the fluid. This one is the continuity equation, your momentum equation, and the energy equation, right? So again I am writing this equation of the RTT equation, Reynolds transport equation I am writing again. So this is your see few of these equation right now you will get to know few things which most probably you have ignored in your basic maths in the engineering. So in the while in the engineering first year, uh, so you have studied about this divergence, convergence, Stokes law, and all these things you have studied. Divergence law, right? But no one, that most of the student will not understand this thing. So that's why it will be a tough sometimes to understand this thing. So not an issue. So we will try to understand in simple way. So now this is the RTT equation. So in this RTT equation, basically first I will be talking about this conservation of. So after this, initially I'll deal with this continuity equation and momentum equation. After this, we will be solving some numerical problem, right? Conservation of mass. So in the conservation of mass, what is the property? What is the extensive property here? This means capital N is the extensive property we have studied earlier. N is the extensive property, or N is the intensive property, that is N by mass. So here N means your mass, or N means mass by mass, which is your 1, right? So in this equation, if I put this equation, what I will get? This is dm by dt. This will be, in place of n, it will remain same, plus uh, v n into dA. So can you tell me one thing? What should be the value of dm dt of a system? This is the, say this is the system. Can anyone? So you know this thing. Everyone know this thing. What happens to a mass? Universal law is there. Anyone? Please. It can be wrong, not an issue. So just try to answer. Okay. You just think. Okay. So let me answer this one. So say we can know that like mass of a system always remain constant, just like that of energy. We know okay, energy can neither be created nor be destroyed. So similarly here, it's a system means a universe you can talk about. In universe, mass cannot be destroyed. So whatever may be the mass entering into the system, I'm talking about the whole system. So it can be coming out. So it will remain fixed, so there will be no change in the mass with time. So that's why this thing should be 0, right? So the equation should be looking like this. Now just I'm assuming that this body, this control, this system, in this system I am just assuming two things. One is that non-deformable control volume. That means the small part or the small square or anything, any shape, which is we known as control volume, which we have taken, if it doesn't deform with time, then it is known as a non-deformable control volume. And next is the stationary. That means its position is also fixed. Its position can't be changing with time. That's why this is known as a Eulerian approach. In the Lagrangian approach, we consider whole the system as a fixed body. But in the Eulerian approach, inside this body, we just take a small body and consider it is in the fixed position. So that is the Eulerian approach. That's why these two assumptions we take for the derivation of this conservation of mass. Okay, please remember these things: non-deformable control volume and stationary control volume. So as the control volume doesn't change with time, so what will happen? Uh, so this integration sign, what we can do, we can just put this integration sign before this ddt. Right, it is control volume, right? Again, this one is your control surface. So to convert this control surface into a control volume, I think that most probably you have studied this in maths. So to convert a control surface into a control volume, what we need to do? We need to use divergence theory. So please look into this divergence theory in the maths book, you will get it. So I just write this thing into this control volume approach. So we will get CV rho. There will be divergence theory, so there should be divergence. Sorry, and this is not there because we have considered n as 1 into dv. Got it? So that is how I convert this CS into CV method. So now can I write? I just take the integration, or I have write this as ddt of rho plus, can I write? Okay. So ultimately what I get del rho v del dot. This is divergence. Remember divergence equal to 0. So this is how your continuity or conservation of mass equation come. This is basically a conservation of mass equation. Any confusion up to this? Please let me know. Please let me know. I am giving you 2 minutes time. So please look into this 2 minute gap. So please look into this, and after that, because if this thing is okay to you, then you will clearly understand the other concept like this momentum equation and this thing. So this thing, this conversion, this in the black line, from this to this, whatever may be the conversion I have done, this is based on divergence theory, which state that if you convert this dA, which is area means control surface, into control volume, so what you need there should be a divergence. That is it. So please look into this thing. I am giving you 2 minutes left. If someone has any question, he can open this mic and raise the issue. Hello. Good evening. Hi. Yes. Huh, huh, huh. Hmm. So the answer you were talking about, what the question that is given in the assignment? So which question? Week 5, question number 10. That is the question. Let me note down. Question 10. And week 5 and week 6? 1 and 2. Huh, 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 huh. So in the solution, whether they have provided you the full solution and only the answer. Okay, so the thing I have to check this thing because I think that maybe the issue is that somehow the option they had put is by mistakenly they have given the wrong option. In most of the time, this thing is happening. In one of the classes also in the last semester, I have seen 3 to 4 questions they have misput the option. So that option can be that thing can be happen. But can you check your answer 2 to 3 times that you are correct in the procedure? Everything? Uh, uh, huh, it is said. Huh, huh, okay. Uh, uh, okay. So, okay. Okay. No need to worry. I will just convey this thing through the TA who is who is giving this and solution. So the thing is that the group is different. Like I am taking your online session, right? I am one of your TA, but the TA who is preparing this assignment solution for assignment question for you are different. So I need to talk with them. Maybe it's a mistake from their side. I don't know. Okay. So I'll surely look into this. And another thing is that you can raise doubt also. You can write a mail, so that can write a mail or you have all. Huh. Okay. Okay. The thing is that that TA actually I have meet most of the TAs. So what happened actually in the last 1 week, most of the TAs are busy on a symposium, right? So there was a conference like on the IIT Guwahati, so everyone was there. So that's why no one is able to answer this. Even you can see that my classes was regular classes was on Saturday 3 to 5. Uh, but just uh, uh, hmm, uh, oh, yes. Yes, definitely. Definitely, it's no need to worry because as you have already raised the concern in the through mail or this, even you have said to me, so no need to worry. From the NPTEL side, it will be corrected. It will be rectified. as soon as possible. So you just no need to worry because it's a mistake from their side. So I'll again check and I will talk with them. Okay. Okay. And not an issue. If such an issue comes, you will definitely tell in the class. So so any up to this any confusion? So I'll okay. So I'll move to the next one. Uh, okay. So so up to this, you just remember this final format of the equation. So this is this equation you just remember because in the next slide I will elaborate this thing. So see in these three equation, this is the conservation of mass, conservation of equation, and conservation of energy. So in these three equation, mostly if I talk about your BTech level, in the BTech level you will be mostly dealing with this conservation of mass, which was quite important for your BTech level. But if you are planning to have masters or PhD level, in that level the momentum equation and energy equation are quite vital. That doesn't mean that in BTech level it is not necessary. It is necessary, but our main focus should be on this conservation of mass equation. So you should have to be more confident on this conservation of mass equation, right? So I'm writing this thing again. Sorry. So this is the equation I have got, which is our conservation of mass equation. So say I just assume that this velocity v. So this is a vector. So this vector means it can be in x direction, y direction, z direction, right? So I assume this there it has three components, one in x direction, one in y direction, and one in z direction. So I can assume this as u in the x direction, v in the y direction, and w in the z direction. So this equation, I'm talking about this equation, I can write in this form. This is rho plus this is divergence. What does this mean? This basically means your ddx of I cap plus j cap plus, and this is a dot product. Okay, and I can write v as u I cap plus v j cap plus w k cap. Okay, so that is the thing. So now if I this thing, so what I will get this as this format ddx of your rho u plus ddy of rho v plus ddz of rho w, that should be equal to 0. So this is the equation I am getting. From this I will get this thing. So the important thing is that you please remember this thing. So that will be quite easy for you. Now the thing is that say you most of you know this derivative formula for this derivative of uv. First you have to do u, then derivative of v plus v, derivative of u. The same thing I will write here. From this thing can I write? Initially I take the rho du dx plus u. Similarly, in the next part also, I can write plus rho dz plus w d rho. You got it? Now, see, I just do one thing. I just write the rho term in a single place. Sorry, u v plus you will get rho term. Okay, so this is the equation you will get. So see, this is nothing. This from this equation you can easily derive this thing. So where I just write this derivative form in this way, and after that this is the simple derivative formula. Okay. So see, if I just do one thing, I just divide it into two part. This one is part and this is the next part. Say if you say for an incompressible fluid, what is an incompressible fluid? Can anyone tell what is mean by an incompressible fluid? Incompressible means density should be constant, right? So if the density is constant, each derivative should be 0, irrespective of if you derivative it with respect to t, with respect to x. Arey, sorry, someone please check your mic. Noise is coming. X, y, z. Whatever derivative you do with this row, you will get 0. So that means for incompressible things, this whole term should be 0, right? So only you will get this thing as 0. So this part is thus this part is quite essential. So as in your cases or BTech level, you will find most of the fluid as incompressible. So you will get only this thing. So in the from this bigger equation, you only require this thing. If the fluid is incompressible, right? So up to this it's okay. Now the thing is that I'm just showing you one more thing. Basically, this thing generally is represented as D. D, okay, capital D. Capital D rho dt, which is known as total derivative. This whole term is known as the total derivative. Total derivative. So just remember this name. It is not necessary that much. So I can write. So in case of incompressible fluid, the total derivative should be, what should be the total derivative, Ayush? It should be 0. Very good. So in case of incompressible fluid, the total derivative should be 0. So this total derivative term, I think you have also studied in this acceleration term. In the fluid, when you study about this fluid mechanics, you have studied the acceleration at a point, right? If you see, in place of rho, if you consider a, you will see, you will get the acceleration dA dt, rho a, rho t, u dA dt dx, x component, y component, z component, same thing na. So that basically means it is the total derivative of the density, acceleration, function. That's almost same. So only the variable is different here. Now, what this thing, du dx dw, what does this means? That is a quite important thing. Why we need to study this thing? So this thing basically means your, this is your velocity gradient. Yeah. So this is basically corresponding velocity gradient, or most or also some people say it is also tensor. It is your stress tensor. Okay. So velocity gradient, this thing you please remember. So why this thing is required, this formula? So if in a question, in a gate question, if it is given, the fluid is incompressible, it is given. So you get in the question they will give this velocity v equal to, like in this v equal to 2xi plus 2yj plus 2zk. So you are asked to find this accordingly. You can find out now. To check, say the question will be coming like this. So this equation will be given. You need to check whether the summation of all these things should be 0. If it is 0, then means the continuity equation is followed. Else, it will not follow. So question can be like that, or in the question can be, it is given like this way, v equal to 2xik plus 2yjk plus unknown a value w k cap. So in the question I say it is an incompressible fluid. So what should be the value of this unknown w? So you can find or not, or I'll show you an example. Is it necessary to show an example, or up to this it is okay? Oh, okay. Okay, okay. Say in a question it is given b equal to 2x I cap plus 2y j cap plus w k cap at point 1 comma 2 comma 3. Okay, 1 comma 2, that means x equal to 1, y equal to 2, z equal to 3. Given it is incompressible, so w equal to what? So what you need to do, from the conservation of mass, what you have, I can write the conservation of mass equation from the beginning. Say you forget this equation, that's why I am writing rho v. So as it is an incompressible, that means this term will be 0. So that means basically also rho is a constant, rho will come out, rho into That means, or this means v means du dx plus dv dy plus dw dz is equal to 0. Say, okay, sorry, it means 2wz. Okay, so I have to now I can find out du dx. What is u? Ayush, can you tell what is u, what is v, and what is w from this equation? So v is basically v equal to, how can 2 x y 2. So I can find out the value na. So it is 2. Say I just write it as here z. I just give it z here for your understanding. So dv dy, what it would be? 2z. Next dw dz, it should be 2w, right? So now the thing is, a point is given 1 comma 2 comma 3. You can put 1 comma 2 comma 3, no need to point, nothing is there. Similarly here 1 2 3, if you put only in the z you need to put, so it would be 6. Here 1 2 3, no need to put anything. So in this equation I can write now 2 plus 6 plus 2w equal to 0, or 2w equal to minus 8, or w equal to minus 4. You got it? So these types of question can be asked. So I think it is okay. So how, from where, see, I am just one thing. So what I did from the RTT equation, Reynolds transport equation, I just consider the property for the mass conservation. So it should be mass. So it is m, and n means mass per unit. So what is n? N means intrinsic property, right? N by mass. So that's why it is n, and putting we will get this value, right? So I am similarly I am not writing this thing in whole. I am just showing you the fundamental thing, because already this derivation has been done by Professor Chakraborty in the class. So that thing dn by your dt, this is your Reynolds transport equation. Got it? So that is the Reynolds transport. So assumption, what we need to assume, the previous assumption should be there. Only what should be n? I am talking about this conservation of momentum. So can you tell what is momentum? What is momentum? Anyone? Momentum means mass into what? Mass into velocity. So see, uh, it is a control volume. So what mass I am talking about, that is not clear. So that's why I just write a small mass dm into velocity v, integration. This is n. What is m? M basically means by mass, so only we will get B, right? So this is my assumption. If you put all these thing and finally you will get a form of the equation. So should I need to show the full thing, or I should write the only the final form? It's up to you. Just let me know. Okay, I am writing the final form. So the final form should be here, in place of it should be a this term. Say this term will be put here. So which is your rate of change of, this is your momentum by t. That means what? Rate of change of momentum, right? So can you tell me where you find this rate of change of momentum? What basically rate of change of momentum indicates? You have studied Newton's law. From the Newton's second law, what it state? What it state? Can you remember this thing? The rate of change of momentum is directly proportional to direct. So what is mass into acceleration? What is it? It is force, na? Rate of change of momentum is directly proportional to applied force. So basically the first term is your applied force. So this is the total force. I can write total force in the CV. Okay. And the final form should be CV ddt of rho. What is it? I'm writing is rho v, or so which would be easy for you to understand. Okay, rho u. I am just writing for x direction. Okay, plus del dot rho u v into, this is the equation you will get. So now this force, this thing. So this is the force. So this force basically include two force, which is the surface force plus body force. So the no need to remember this form. Just I am saying from where this thing is coming. Basically, you understand what is the, this is the first part is the rate of change of momentum, which is the force, and next is the derivation like the previous one. So this force include two terms. One is the surface force, next is the body force. Okay. So this surface force, I just write this surface force. Say if someone talks about the surface force, what basically the surface force include? A shear term can be include, right or wrong? In the surface, what type of force act? Any idea? Anything you can tell. Not an issue. Stress, right now. If there is a surface, what types of force? Stress. So I just represent the stress term, and for your understanding, though there is a this term has a quite more significance. So for this significance, you need to go through the main courses, main derivation. But from the fundamental thing, I am just explaining this thing to you. Okay. So basically, This is the stress term. So as it is a stress term, so see, stress. So say what is stress? Stress means force by area. Yeah. So if it is a stress, if I it is in force term. So if I have to write it in terms of dA, right? Right or wrong? So again, if I have to convert it into, now it is in area means it is in control surface. So to convert it into control volume, I have to put a divergence before tau, and then it should be in, right or wrong? If area you need to convert it into volume, you should have to put a divergence before this thing. You got it? The same thing what we have explained in the earlier, say, control surface to control volume. What I did, rho v dA. Area, I just change the area into volume. What I need to do, I need to put a divergence before. Now it is clear. It is a divergence theorem. Divergence theory. So now in place of surface I can write CV del T dV, and the body force can be written as, body force means whatever be the force there in the body. So this is body force, say B. I represent this body force as this one, B. Up to this, any confusion, please let me know if there is any confusion, or else I will move to the next part. Okay. So now see, you all the whole the equation is coming in a single format, where in each and every part there is CV, integration of CV. So I can write from the right hand side. I first write down the right hand side. Is it okay? This B means body force. Force by volume. Okay. So this is it. So I am moving to the next slide. Or 5 more minutes, and after that we will move to the numerical. Hmm. So the equation that is coming here, that was coming earlier, ddt of rho u plus rho u into v equal to this into tau plus v, right? Now what this tau, because this tau is an important in case of your fluid mechanics, because the tau is though it is a shear, it is a stress tensor, so it depends on a certain factor like your mechanical and thermodynamic property and many more properties. So for this we need to know So you know what is a Newtonian fluid? Do you know what is a Newtonian fluid? So please tell. Uh, Viscosity, not viscosity. It is you, you just that is the shear stress is directly proportional to your velocity gradient. All these things, not a directly proportional to only yeah, all these things. So basically, in this equation, it was your velocity gradient, right? And also see what has happened in the Newtonian fluid. In the Newtonian fluid, the stress tensor, the tau. Tau is symmetry. Symmetry means what is symmetry? Just say. Not sorry. This is not the correct way to show. Say if this is a block, this is a plate, na? So you just see this thing. Say this is tau x y. So before this, let me show what is tau x y. So what x indicate? X indicate direction normal to the surface. Surface, and y means direction of force. Okay. So say so that means what it indicate? It indicates the direction of the normal to the surface in the x direction. It is in the x direction, right? And the direction of force is in the y direction. So basically, if I have to plot the tau, so the tau should be in this direction, tau xy, right or wrong? X mean in the normal to the, yes or no? Please check and let me know. Hmm? So then what is tau yx? Tau yx means, so y in the y direction there is the no, direction normal to the surface, and the direction of the force is in the x direction, right? So in if the magnitude of both these two things are equal, then it is a Newtonian fluid. You got it? So tau xy or tau xy or tau yx should be equal in Newtonian fluid, for Newtonian fluid. So please, just in a simple, I am saying this thing. You please follow this lecture, class lecture. Okay, in the class lecture that has been provided in detail. As my objective is to show you some numerical solution, that's why I am just showing it in a simple way. Apart from this, in only Newtonian fluid, you find the stress tensor is symmetric. In which fluid the stress tensor is symmetric? In the Newtonian fluid. In all other fluid, it is not symmetric. Now you will study another type of fluid for fluid mechanics. So that is your Stokes fluid. You have studied about the Stokes fluid. So basically, Stokes fluid is that in the Newtonian fluid. I just from the Newtonian fluid, some fluid we can define as a stroke fluid or Stokesian fluid. It's like you have subset and superset, subset. So I'm just giving you an example. Like family. A family is a set, and Ayush is a subset of the family, right? Or your father is also a set of the subset of the family. So an individual member of the family is a subset of the family. Like that way, the Stokesian fluid is a subset of the Newtonian fluid. So in the Stokesian fluid, what happens? So a scientist named Stokes, so he has found out something interesting here. So what he found out? He found out that if any Newtonian fluid mechanical pressure and the thermodynamic pressure should be equal, then it is known as a mechanical pressure equal to thermodynamic pressure. Then it is known as Stokesian fluid. But first thing is that it should be a Newtonian fluid. Okay. So what he did, he do a lot of experiment, lot of research. So he just say people that I have found out something interesting. No need to remember the whole thing. He just give this tau. In this equation there is tau na. So the scientist, he just elaborate this row. So he said that this thing can be written in this format. What? P into small delta. Delta is a small change, right? Plus small delta. So no need to remember this thing. I am just showing for your understanding. Sorry. So this equation he has given, right? So it's a formula, no need to remember. He just give a formula. He said that if a Newtonian fluid follows this thing, then tau can be written in this form. Or say in some places you will find this in term of Ij minus P. This is P. Ij. Only for derivation this thing is required, nothing else. This is J. So you will find this thing, maybe some of you find this thing boring. Yeah, I know that that is boring, but it is needed to understand. Only the concept is needed. What is P? The P is your thermodynamic pressure. Okay. Next, this lambda. This lambda is your bulk viscosity. And that means the viscosity of the whole fluid. V I know velocity and all these things you know. Now what Stokes proposed? So the stroke proposed that for a Newtonian fluid, if this thing is followed, that means P mechanical equal to P thermodynamic, then I can write this stroke. This is bulk fluid viscosity, na? This bulk fluid viscosity follows a formula which is minus 2 by 3 of mu. If a fluid follows this thing, which is the Stokes hypothesis. This is Stokes hypothesis, not law. Please remember, this is Stokes hypothesis, no, not law. Ayush, any confusion up to this? Huh. So why not law? So in the why not law, I just tell you, if you remember that in the fluid mechanics you have studied the drag force on a spherical particle. I just draw you one thing. This is not required. If a circular ball is flowing through a fluid, you find this Stokes law where FD is 6 pi mu RV. Like that, you find this thing. Maybe I don't know. In fluid mechanics, have you find this thing Stokes law? So that's why this Stokes law, huh? Okay. So that is not necessary. Actually, the thing is that if I talk about the Stokes law and the difference between the Stokes hypothesis. So the Stokes hypothesis is basically based on this Stokesian fluid, where he has discussed about this what should be the tau. So he just elaborated this tau. For this he said that to elaborate this tau, I have found out that this lambda equal to minus 2 by 3 of mu. That is his finding. And so he just give the hypothesis which may not be universally true. Hypothesis means you are just difference between law and hypothesis is like that you are going to a station, railway station. So you were suggesting your friend that please do not go by the main road, please take the bypass, because in the main road there will be traffic. So this is your hypothesis. Maybe in a specific day there will be traffic, but in other day there will not be any traffic. So sometime your hypothesis may be correct, sometime your hypothesis may be wrong. Okay. So hypothesis, difference between hypothesis and law, is it clear? Okay. So up to this it is the, so from this thing he has derived this equation. So just if this thing, this tau, he after that they put this tau in this equation and got an equation. The equation is known as Navier-Stokes equation. Navier-Stokes, because though Stokes has given this thing, another scientist Navier, what he did, he just put this thing here and say that I have found out the formula which is known as Navier-Stokes equation. So that is not being discussed today. So we will be moving to a numerical problem. Numerical, not some question based. Okay. Okay. So uh, before this question, up to this, what I have told you, I think it is clear to you, right? So anisotropic or so see, isotropic fluid means the properties are identical in all direction. So an anisotropic means the properties are not identical in all direction. So then this is the Navier-Stokes equation. The Navier-Stokes equation basically comes from your continuity equation, right? So from the Navier-Stokes equation, NS equation, So though I haven't derived this thing fully, I suggest you to please go through this book. The first is that the fluid properties varies continuously with time. Okay. Next is a properties are uniform at a point. Next is then it should be an isotropic fluid, and what type of fluid should be it should be Newtonian or non-Newtonian? Newtonian Stokesian fluid behavior. So what will be your answer? So these are the assumption. So because it should not be anisotropic, it should be isotropic. So that's why the correct option is option B. Okay. So next question. It's an important question. Let us see how you answer this thing. So which will be the correct answer? Option B. Very good. So already I have discussed this thing. That means for a fluid to be a Stokesian fluid, first it need to be a Newtonian fluid because it's a subset of the Stokesian fluid is a subset of the Newtonian fluid. Next is that it should follow this property, which is the mechanical P mechanical equal to P thermodynamic pressure and mechanical pressure should be same. The main thing is that it should follow the hypothesis, which is your bulk viscosity or second coefficient of viscosity. Both thing people use, but I use bulk viscosity. This should be minus 2 by 3 times of dynamic viscosity. It is your okay. This is your bulk viscosity. So I'm moving to the next question. Hmm, it's an important question. So just now I have given you this thing. Yes, sorry, one thing. I just forgot to write down this whole form of the Navier-Stokes equation. So I'm writing this Navier-Stokes equation for your understanding. Do I need to write? Maybe I have written or not. I have to check. Just one thing. Let us check. This equation I am just putting few things so that it you can easily understand this thing. In the Navier-Stokes equation, after this, as from this Stokesian fluid formula, finally after so much of derivation from this part, I am talking about this part. Okay, So what they got this is del P pressure plus mu del square V plus this body force. Body force means rho G. You got it? So this is the form of the final form of the equation. Is it okay? Hmm. So I am just writing this thing so that you. So what I got d dt of rho u plus into minus del p. I'm just writing in the x direction like this way the equation. Okay. So I am doing one thing. I just write it in a vector form. So I just convert all this thing into v. Okay, this is the form of the equation. So this is your Napier-Stokes equation. So under what condition does this Napier-Stokes equation converge to Stokes equation? So this is a quite important. Just let me give this for your better understanding. So this thing I just write. So let us assume this density is constant. So can I write then this thing? I just put the density here. Can I write? Hmm. So this thing. Now what I said in this equation, this part is a total derivative part, right? I have said in the few slide back that this whole thing is known as a total derivative. Forgot about this thing. What is dv dt? Velocity by time means what is no dv dt velocity rate of change of velocity with time means your velocity gradient means so this is your local acceleration and this term is also acceleration but this is your convective acceleration. See why such thing. So in the momentum equation, so in the momentum equation basically means rate of change of momentum equation, which is your the first part in the momentum equation. What is the first part? Rate of change of momentum, right or wrong? Yes or no? Just tell. In the left hand side of the momentum equation, it is the rate of change of momentum, which is basically your mass into acceleration. So if this is acceleration, this part is the acceleration, density means the mass is coming into account. So mass into acceleration, this is force. Similarly, this is acceleration, this is mass, density. You got it? So that's why this is the force. Okay, so basically these two terms, acceleration term, what they indicate? What acceleration indicate? Just tell from the Newton's law or second law. Momentum, a rate of change of momentum from where this thing comes. What is the first law? Can you remember? Okay, not an issue because most often we forget this thing. But little bit you know, you remember. I know that you people always know all these things, but you just forgot right now. Yeah. Yeah. Yes. So, what is the in a word? What I can say this? What is this phenomenon known as? This is known as inertia. Okay. So, basically the first part is represent your inertia. So, for a Stokes equation, what is there is a Stokes equation, not hypothesis. Remember, it is quite bit confusing. In the Stokes equation, so it should follow the Stokes flow. Flow condition whom it should follow the stroke flow condition. What it state that in the stroke flow condition the inertia is negligible. Inertia is negligible. Inertia is negligible basically means this part na this first part should be, if there is no acceleration that means the system is, there is no inertia, right? This, if there is no acceleration, what it indicates? There is no inertia. Like you said that if a body is in rest, it will continue to be in rest. So up to this, it is okay. So what you see that the flow when the flow inertia is zero, yes, it can be a case. Next is that the fluid is not accelerating. If it is zero, that means there is no acceleration. So is it correct or wrong? It's correct. C option, the fluid is non-Newtonian. Is it correct or not? Because it should be Newtonian. The fluid is non-homogeneous. It is correct or not? Because so the correct answer will be option E. We got it. So as it is zero, so what should be the equation? Final equation: zero equal to minus. uh, So please, Ayush, please remember this format of this equation, Navier-Stokes equation. It is quite necessary. If you remember this thing, majority of the problem will be easy for you to solve, right? Uh, so option E is the correct answer. Uh, so you can easily answer this thing. Huh? Okay, right. Hmm. Hmm. Next, I'm moving to the next question. So it is quite easy because already I have discussed about this thing. Please try to answer. It's talk about a Stokesian. Yes, it is follows because if it is a Stokesian fluid, the always the P mechanical should be equal to P thermo. Already I have discussed. That means the pressure appearing in the stress tensor part and the pressure from the thermodynamic part should be identical. Okay, so it should be false. Next question. It's a simple question but a tricky one. So Which of the following is wrong about viscosity? Say, I am just a one hint of the question is that it is a multiple choice. It is a multiple choice question. Not it has do not have a single answer. This is the hint I am giving you. B, C, and D are wrong. No, partially correct. Option D. Option D is correct. Option D is not the answer. See, only A, B, and C are wrong. So the correct answer is ABC. How? Now the question is how. That is the thing, na. The question is the shear component of stress and normal component of stress. Both these things. That is quite important here. So, can you assume why your option is not correct? No need to worry, just try to understand. Else I will answer for this for you. Okay, so see, now I am talking about shear component of first option. Say shear stress. So in the Newton's law, from the Newton law of viscosity, what we have? Can you tell? So this one is tau, is mu, this one, this is xy. So that means this one is your velocity gradient perpendicular to what? Perpendicular to flow. So I can, so because this term, this del u del y, basically this is the shear stress due to viscosity, right? This is your, from the Newton law you study na that the viscosity is proportional to the shear stress. So it is, if it is a Newtonian's law of viscosity, then option A is correct. But in the question, nothing is mentioned whether it is Newtonian or any other fluid. Okay, so either Newton's law of viscosity is followed or not. So that's why this option is not fully correct. If the option is, if only is given, if the word only is not given, then option A is correct. Okay, so an word only is quite important here. Now, from the Stokes law, what we have written, as you just a few moment back, I think that you have written this thing P del uj del x plus like this thing. It is already. Do not say I am not uh, remembering this thing. I just write it from a copy because I already I just forgot this equation. Okay, so I expect that I already know that many of you do not remember this equation, but only the fundamental is required here, right? So see, here if you talk about this equation, here there is this equation came from this Stokesian fluid, where there is two things. One is P mechanical and what is there? P mechanical and P thermodynamic. Okay. So thermodynamic, forgot about these thermodynamic terms. Now I will talk about these P terms. Say, see that here U and Y. Just say me one thing. What is U? In which direction? U is in X direction. V is in Y direction, right? Uh, So see that in this, if you recall this thing, you see that u is there and this is derivative with respect to y. That means the flow is in the x direction, but the derivative it changes is taking with respect to y direction. That means it's a shear stress. Okay. But if see, if I write here in this equation, there is two terms. One is in the x direction and another is in the y direction, right? So that basically what that basically indicate. Hmm. Yes. So, so that's why option B is not correct. All because of only the word only. So the third option is the viscosity is related to the normal component of the stress when the fluid is rest. So there is no such component where the fluid is rest. If the fluid is rest, then V or U should be zero. So there should be no component. So that's why this is also wrong, wrong. So the sorry, not wrong. No? The question is which is the wrong, which options are wrong. So the correct is option A, B, C are the wrong option. So the correct option, the correct answer is the viscosity is related to both normal and shear component of the stress. Is it clear? So I'm moving to the next question. Hmm. It's a simple question. Please try to answer. Three more question. Why it is false? Sorry, I'm not able to understand. I'm not able to hear you. You said it is false. Do not. It's so question is we do not have to be necessarily restrict our to any special type of fluid. No, actually we have applied now. We have only considered that it should be Newtonian. So already we have considered. So sorry. Yes. Uh, you got it now. So it is option A. Uh, so this is the next question. So what we can say that the Newtonian Navier-Stokes equation in the last question, it can be applied to any fluid without restriction. But the condition is that it should change. Like the tau is changing or this thing will changes. Okay. So just see one thing. Let me make it clear in the last equation. In the Navier equation, just another thing I just forgot to mention. This is Navier equation, not Navier-Stokes equation. Okay. Hello. See this thing. This is Navier equation. So if it is talking about this Navier-Stokes equation, then only your Newtonian is okay. But as it is talking about this Navier and Navier equation, so it consists of both Newtonian, non-Newtonian, viscous, elastic, every types of fluid. So there is difference between Navier and Navier-Stokes equation. So in the Navier-Stokes equation, specified it is for Navier and Stokesian fluid. So question 7. So the question 7. So see, the question 7 part has I haven't though discussed about this part because it is the energy equation. Uh, I will I will explain this because that is not that much required in the today's class, so I haven't discussed. So basically, this is your energy equation that you will get. Okay. So this is your total derivative or rate of change of energy of the system, right? And this is your surface heat transfer, or I can say it is conduction heat transfer, not surface. I better to write conduction. This is Q generation, sorry, heat generation. Heat generation, and this is your viscous dissipation. So basically, in an energy equation, so it consists of three parts: the surface heat conduction, uh, volumetric heat generation, viscous. So this is the things. So what should be the answer? Say internal energy. What is internal energy in a system where there is internal energy generated? Internal energy is generated because of conduction. We have studied in the first classes. Forgot about this equation. If you do not remember this equation, still you will able to answer this. How? In the first two classes we have studied that if we supplied a heat to an wall or a metal piece, so there will be conduction. So basically the energy is storing into the system. That's why there is a temperature gradient, right? So the surface heat transfer should be there. Because of the surface heat transfer, energy generation will be there. Volumetric heat generation. So say if current is passing into the system, there will be heat generation. Yes. So next is the viscous dissipation. Viscous dissipation means if I talk about a tire. So if you ride a cycle for a for 15 minutes, and after that if you touch the tire, you see that it is getting heated up. That means energy generation. Why this is because of your friction. As it is in the solid to solid, so it is friction. But if it is in liquid, there will be viscosity, right? So the correct option would be option A, B, and C. Got it? Last question. Hmm. So see, the question is that during the fluid flow, viscous dissipation may not always give rise to heating. Is it correct? That means a fluid is flowing, so at that moment the heat, the because of the viscosity, there is no heating. Is it correct or not? What do you think? It's like it is false. Yes, because it's like during cycling. The question is like during cycling, the tube will not heat it up. Is it correct? No. If you ride a cycle, it will definitely. So this is correlated with the cycle. Okay. Next is that viscous dissipation occurs as different fluid layers slide over one another and the corresponding work is converted inversely into molecular form of energy. What do you think? This is the thing. This is the viscous dissipation. Why there is energy generation because of cycling? Because as the tire comes in contact with the solid surface, so what will happen? There is because of this sliding, the work done by you is converted into energy into this heat energy into this tire. Similarly, if the fluid is flowing over a surface or over another fluid layer, what will happen? It will slide, and because of this, work is getting converted into energy. So the statement 2 is correct, right? So the correct option is option option D. So I think it is clear. So viscous dissipation, it is quite essential. So you see, the viscous dissipation is important in lubrication system. Like the lubrication system, like in the engine, there is lubrication, na. So that is less lubrication. There are many systems where there is a significant lubrication required. In that cases, you will find this viscous dissipation. So last question for today. So already this thing has been discussed. So it's a micropolar fluid. So it is a certain types of fluid. What is micropolar fluid? So it's a type of fluid which contain microstructure. Like if a fluid contain microparticle, particle or structures. Like if I talk about blood. So though blood look like a structure, blood is a particle, microparticle, like then suspension. That means if I talk about in milk, is a suspended particle. In the milk there is suspended particle. So maybe I'm not sure. Just check whether milk is a suspended particle or not. I just forgot about this thing. Next is a crystal. If you put some crystal in a fluid, so these types of fluid is not a micropolar. If some a microparticle is there, which are then it is a micropolar fluid. So here there is a tau ij and tau ji is equal. So is it correct or not? It is correct only for, I just say that tau xy equal to tau yx for uh, so for all other fluid it is, got it? Hmm. So any confusion up to this? So this is I uh, so you need to remember nothing else we can do. So already you have the previous class notes and all these things. Hmm. So up to this any confusion? So can I wind up this today's session? So our next session will be on Saturday, on the next upcoming Saturday. So Monday, as the today session is on today because I have just shifted it because of my some issue. So I was busy in some conference like related issues. So that's why I have just shifted it to today. But in the from the next class onward, it will be on Saturday from 3 to 5. So hope you will join. And if you face any issue, you can mail to me. Okay. So have a good day. Till then, bye. Yeah, but huh, hmm. Yes, yes, just a minute. Let me first stop this session and after that I'll talk. Huh? Wait 1 minute. Just wait 1 minute.